Hi, welcome to another episode of Mr. Avila Physics. Today we're going to be talking about potential energy, both gravitational and elastic. In an earlier video, we have discussed how objects have energy because they're moving, and we call that type of energy kinetic energy. But it's also possible for an object to have energy depending on where it is located or its configuration around other objects or their surroundings. This type of energy is called potential energy due to its position. Okay, now in this video we're going to be talking about two types of potential energy, which are gravitational potential energy and elastic potential energy. Now the most common example of potential energy is gravitational potential energy. Gravitational potential energy has to do with an object's position based on Earth, based on a reference point on Earth, right? For example, a heavy brick that you hold it up high has potential energy because it is away from the floor. It is higher than the floor, so it has potential energy. Now, how do we know that it has energy? Well, that brick has potential to do work. If that brick is held up high and then I release it, then it would fall, and then if it hits something on the ground, for example, a stake or a nail or something, then it can dig that nail into the ground, or it can dig that stake into the ground. So it can do work on another object, which is why it is said that a raised object has the ability to do work and therefore it has potential energy. But how do we find the value of potential energy? Well, let's see if we can use work to find out how work and energy are related. So if I want to lift an object of mass m, then I need a force at least equals to its weight, right? And if I want to lift the object without accelerating, then I need a force F exactly equal to the weight, such as this, right? My hand is applying a force equal to the weight of this object, and I am moving this object from a position y1 to a position y2. Okay. Now, if I do this, if I take my hand and I get an object and I lift it from y1 to y2, then I'm doing work on this object. Why? Because I'm applying a force through a certain displacement. Now, how much work did I just do? mg times h, right? Or mg times y2 minus y1. So my work and the displacement are in the same direction, so the angle between the force and the displacement is 0. The force that I need is the weight, right? So this force right here is the force that I need. This is Fx, and this is the displacement, right? So I am doing an amount of work equal to mgh. But at the same time, gravity is also acting on this object right here, right? And gravity is also doing work on this object. Now, how much work does gravity do on this object? Well, we have to find work. We do Fd cosine theta. The force of gravity is mg. This is the displacement, right? And the angle between the displacement, which is upwards, and the weight, which is downwards, it's 180. So the work done by gravity is negative mgh. So we can say that the work done by the hand is equal to the negative of the work done by gravity. Now, if this object was released from the top, then gravity would do positive work, right? Because gravity would point down and the object, if we release it, it would also fall down. So they would both be in the same direction, so gravity would do work on the object equal to, work is equal to Fd cosine theta. This would be mgh cosine 0 because they're both in the same direction, so mgh. So when the object is released from the top, then gravity would do positive work equal to mgh. So we can say that by doing work in lifting an object, all that work that we do is stored as potential energy, right? Because the object, when it's raised high, if it is just there, it will not do any work. The only way it can do work is if I release it, and then it falls. So just by holding it above the ground, then it has stored energy. It has the potential to do some work. All right, so based on this example, we can define gravitational potential energy as a product of the object's weight and its height above some reference level. Usually the ground, but the reference level can be anything that you decide, okay? So to calculate gravitational potential energy, we do mgy, or we can also say that gravitational potential energy is equal to mgh. Some textbooks use the formula mgy, some textbooks use the formula mgh. They're both the same, okay? So if the change in potential energy, well, the change in potential energy happens when an object moves from a height 1 to a height 2, okay? And that change in potential energy is equal to the work done by an external force to move that object. So in a previous video, we talked about how the work done on an object changes the kinetic energy of an object if that force causes an acceleration. We can also say that the work done on an object by moving it from position 1, from height 1 to height 2, would also change the potential energy of that object. So this is another version of the work energy theorem, where we can say that work is equal to the change in potential energy, okay? And that change in potential energy caused by the external force is equal to the negative of the work done by gravity. Something to think about. All right, let's look at this example here. In this example, we have a 1,000 kilogram roller coaster moving from point 1 to point 2 to point 3 as shown. Okay? What is the gravitational potential energy at points 2 and 3 relative to point 1? What is the change in potential energy when the car goes from point 2 to point 3? And let's repeat questions A and B, but using the reference point as point 3. All right, pause the video here, take a couple of minutes, and see if we can come up with an answer for this. All right, welcome back. Now, if we are taking our reference level as 0.1, then this height right here, this height is equal to 0, all right? So if I want to find the potential energy at 0.2, the gravitational potential energy at 2 is going to be equal to mgh, which is going to be equal to 1000 times 9.8 times h, which is 10, right? The difference from the reference point to point 2 is 10 meters above the reference point. So my change in potential energy, well, the potential energy at point 2 would be positive, right? And this would be equal to 98,000 joules. Now, if I want to find the potential energy at point 3, then I do the same thing, right? Potential energy is equal to mgh, which is equal to 1000 times 9.8 times, but in this case, 0.3 lies below our reference point. So the potential energy at 0.3 with regards to 0.1 is going to be negative because you are below the reference point. So the potential energy at 0.3 would be 147,000, negative 147,000 joules. Cool. So if I want to answer question 2, question B, what is the change in potential energy when the car goes from position 2 to position 3? Then let's just do this in a different color. So to answer question, this is question A, this is question B. To answer question B, and I want to find the change in potential energy, then I got to do final potential energy minus initial potential energy. So what is the change in potential energy when the car goes from point 2 to point 3? So point 3 becomes our final potential energy. So potential energy at 3 minus our initial potential energy at 2. This is minus 147,000 minus 98,000. And this is equal to plus 98,000, 245,000 minus 245,000 joules. Which, does it make sense that it is negative? Yes, because you are losing potential. You are losing height. You're going from a higher height to a lower height. All right. Now, let's, I'm gonna erase these values here and do letter C, okay? So for letter C, repeat parts A and B, but take the reference point to be 0.3. So this right here, this is our H is equal to 0, okay? So if I want to find the potential energy at 0.1, then I do mgh, right? So our potential energy is going to be equal to mgh. Since you are getting higher, going to a higher height, then h becomes positive 15, and this is equal to 147,000 joules positive, which makes sense because 0.1 is higher than 0.3. If I want to find the potential energy at 0.2, then potential energy would be equal to mgh, which would be equal to m 1000 times g 9.8 times 25, right? Because 0.2 is 25 meters above 0.3. And this becomes, right? So 1,000 times 9.8 times 25 gives me positive 245,000 joules, which makes sense because 0.2 is also at a greater height than 0.3. And if we remember, this is also the change in potential energy from going from 0.2 to 0.3. So the potential energy going from 0.3 to 0.2 would be the same magnitude but positive. All right. Hopefully this example made some sense. All right, let's move on. So here's the solution for the textbook. As we can see, we have the same values right here. All right. So let's now talk about the different type of potential energy, which is elastic potential energy. Now, elastic potential energy deals with elastic materials like rubber bands, springs, the string from a bow, right? Anything that is elastic could have elastic potential energy. So a spring has potential energy because when we compress the spring or we stretch it, that spring has the potential to do work, such as this spring right here. All right, we compress the spring, we put a ball on top of it, and then when the spring is released, the ball is going to have a different kinetic energy because now it's going to be moving. And from a previous video, we learned that if the kinetic energy of an object changes, then work was done on that object. And in this case, the work was done by the spring. So that means that the spring exerted a force through a certain distance on the ball, and the ball changed its velocity. So the spring has energy. Now, in order to compress a spring or to stretch it, then we need a force. But springs are unique in that the force needed to compress a spring depends on how far you compress it. So the force that you apply on a spring is directly proportional to how far you compress it from its equilibrium position or its unstretched position, which means that, okay, the more you compress or stretch a spring, the more difficult it becomes to keep stretching it. Think about a rubber band or a resistance band, an exercise band, right? The more you stretch it, the harder it becomes to stretch it more. Or, the harder it becomes to keep it at a certain stretchiness. Okay, so that means that the force needed to compress a spring is proportional to how far it is compressed. This means that the force exerted to compress a spring is proportional. This means that it's proportional to the displacement. So, which means that the force is not a constant force. So we just said that the force needed to stretch a spring is proportional to x, which is F equals kx. But at the same time, right, as we exert the force, the spring wants to resist that change. The spring wants to come back to its equilibrium position. So that means that the spring exerts a force of equal magnitude, but in the opposite direction, right? So that means that the force in the spring will be equal to negative kx. If we compress the spring, we're going to be applying a force in this direction, and the spring would want to go back to its equilibrium position, so also in the opposite direction. So the force of the spring is equal to the force exerted, but just in the opposite direction. Now, in this case, K is known as the stiffness of the spring, how hard it is to compress or stretch a spring. It is also known as the spring constant, okay, or stiffness constant, okay, and it is just that, okay. It's a positive value that measures how hard it is to compress a spring. And x is the distance from the equilibrium position. Whether you are stretching or compressing, x is the same. So how do we calculate elastic potential energy? Now, on a previous video, we talked about the work done by a non-constant force. And a spring the force of a spring is non-constant. So we can sketch a graph and figure that out. So let us use a graph of F versus X and find the area under the graph. So if I have this is the force applied to the spring for a certain extension. So let's say that we stretch the spring a distance X, okay? So in order to find the work, we can calculate this area. So this area is going to be equal to the work done on the spring, which based on the work energy theorem, this work is also equal to the energy stored in the spring. So to find the area under this curve, this is a triangle. The area is equal to 1/2 base times height, okay? So this becomes 1/2 base times height. The base is displacement, the height is force, and we know that F is going to be equal to kx. So that means that the work done is going to be equal to 1/2 kx squared, where k is known as the spring constant again, and x is the displacement from equilibrium. Okay, so that means that we can define elastic potential energy as 1/2 kx squared. Okay, and remember, x can go in either direction. It can be stretched or it can be compressed. The natural length of the spring or the equilibrium position, we usually consider it as the spring being unstretched. All right, thanks for watching. See you in the next video.